Today we'll be discussing Denavit-Hartenberg, or DH, parameter optimization for robotic arm calibration. We're excited to share with you what we've learned on this topic.
In order to understand our project, it's important to know the basics of the Denavit-Hartenberg, or DH convention. The DH convention provides four parameters, theta, A, alpha, and D, to convert a physical robot into a mathematical model. Another topic that's important to understand is joint angles. Here is a 2D representation of a robot. Each joint has an accompanying Q, or joint angle, that together make up the end effector position and orientation, or pose. In order to go from joint angles to an end effector pose, you would use forward kinematics. In order to go from an end effector pose to joint angles, you would use inverse kinematics. Our project uses forward kinematics to calculate the end effector pose and calculate the error between the model pose and the physical robot pose. And this is how it works. So if a user has a commanded pose for a robot arm, the user would input these Cartesian point and orientation, and the algorithm, the inverse kinematics algorithm, would use that model comprised of DH parameters to translate that into actual joint angles. Now, the model would think that the pose was in one position. However, the actual position may vary due to inaccuracies in the DH parameters. This is where our optimization project comes in. The joint angles that are produced by this inverse kinematic algorithm should allow the commanded pose to be exactly the same as the actual pose.
Discrepancies between where the model thinks the robot is and where the robot arm actually is could be a potential problem. Having an accurate model can lead to total workspace accuracy, to be able to command the robot to be where exactly you want it to be. If a robot is handling something dangerous, like a dangerous chemical or material, or doing something that requires high precision, like welding, that if it failed could lead to dangerous problems, having accuracy is very important. There's no room for error.
Which brings us to the motivation of our project, the BYU Mars rover. The BYU Mars rover participates every year in the University Rover Competition and has a 5-link robotic arm attached to assist with tasks, including a decapacitated astronaut who needs water, or it needs to be able to flip switches or type on a keyboard. And having an accurate pose for this is critical, both for safety as well as performing well on these critical tasks. In order to solve this problem using optimization, we have set up the mathematical representation. We want to minimize the error between the pose of our model and the actual pose of a physical robot across a number of different joint angle sets. And we want to do that such that the DH parameters of the physical robot are never more than 5% off of what the model estimates. This is feasible because if someone were to be creating a model, they would not be more than 5% off in their measurements. So the objective here, as mentioned, is to minimize the error. And because the BYU Mars rover robotic arm has 5 links, that translates to 20 design variables with 4 DH parameters each. Given a set of joint angles, we would expect to have an error in position and orientation. These both produce a 3-part vector which can be scaled, added, and normed in order to minimize it as one single value. The problem we decided to use the robotics toolbox to solve. This robotics toolbox is by Peter Cork and is on MATLAB. In the robotics toolbox, we can use simulated robots in order to calculate the forward kinematics necessary to calculate pose. For example, we would have one model robot using the estimated DH parameters and one physical robot, which we derived by taking the model values and perturbing them up to 5%, and then calculating the error in the pose. We would use our optimization algorithm to adjust the model parameters until they match the physical parameters, which is what we would want to do in real life with data. Using the MATLAB platform, we had access to fmincon and fmin search functions, which could provide us the basis for gradient-based and gradient-free optimization algorithms.
The next step of our project was determining which method of optimization we would choose. Our problem is not convex or discrete, which leads to the question if it was differentiable, which it is. It's just a difficult differentiable problem. This led us to determine which method would be better. So we experimented with providing gradients, and the gradient-based methods lend themselves better to greater numbers of design variables, and they handle the constraints much better. The robot we are examining, the Mars rover, only has 5 links, which leads to the 20 design variables and 40 constraints. But there are other robot arms out there that have much more links, which would scale the problem even higher. So we believe that gradient-based methods would be preferable, even though they require more to set up. To be thorough, though, we were going to compare both types of solvers. So both types of optimization methods would be sequential quadratic programming or interior point for the differentiable. And for the gradient free, we are examining the Nelder-Mead method. Providing gradients proved tricky with the robotics toolbox in MATLAB. It limited the method that we could choose because the functions in the toolbox were not able to handle complex numbers or dual types, which eliminated the complex step and algorithmic differentiation methods. This left us with trying to use finite differencing, which, as shown in the graph here, the built-in finite differencing in fmincon performed much better than the algorithm that we wrote. So comparing the other 3 methods, the sequential quadratic programming and interior point with the Nelder-Mead, the gradient-based methods and fmincon using the just the built-in finite differencing were very comparable, while the Nelder-Mead performed slightly worse. This plot shows error being plotted among all of the different DH parameters. This plot shows the total error between each of the 3 methods over various number of poses used to calculate the error. You can also see that it shows the Nelder-Mead performing worse than the other 2 options, and that the error between the SQP and interior point between 20 and 40 was also very comparable. This plot shows the total time elapsed for the optimization among various number of poses used to calculate the error. Keeping in mind what the previous plot showed, that the error between the 2 gradient-based methods for 20 and 40 was very similar. It's just not worth the extra time to do the full 40 poses that we originally were considering. This plot shows the number of function calls for the explained scenarios. And it shows that the lowest amount of function calls for the SQP method were between 5 and 20. This is showing that the SQP is doing its best work in that range, showing that the gradients that it is calculating right there are the best for the SQP method in that area.
So we created a GIF to show exactly what the optimizer is doing every time it runs an iteration. So as you can see, the small movement in the robotic arm here shows the optimizer giving a set of DH parameters and then adjusting them slowly until the error in the pose is minimized. And these are the final results of our optimization. We selected obviously the SQP algorithm because it performed the best out of all of the ones that we looked at. And as you can see, the errors are almost all in the neighborhood of at least 3 decimal places, mostly in the lower 4th decimal place, which is exactly what we want. We wanted here, our goal really was to make sure that we could provide any physical robot or any physical model and have it be adjusted according to data or a simulated data, and get basically no difference between the DH parameters of that physical robot and the model. This will have a large impact on the Mars rover project, which also uses DH parameters to model our robot arm. So we tried to collect real data in the RAD lab, and we spent about 8.5 hours trying to do that. But in the end, we could not get the Mars rover arm to cooperate and move in such a way that we could collect data. So we went the extra mile on our project and basically prepared it to where all that would be needed to actually implement this in real life would be just simply collect the data from the arm. So actually gathering the true pose and associated joint angles, and then running the optimization.
To wrap things up, the implications of this project is that the results indicated that the optimization can successfully calibrate the model DH parameters to within 1% across 20 unknown physical parameters. So there's very good results, very accurate. By taking a relatively small number of data points, only 40, it allowed us to be able to create a full workspace optimization of those DH parameters. This type of optimization could fill an interesting need in calibrating robotic arms and attached sensors. This could reduce engineering time calibrating these different devices and could save money. Our project reinforced the idea that gradient-based algorithms, while harder to implement because of the need to get accurate gradients, they're more accurate and less computationally expensive than the gradient-free variations. Thank you for your time.